Hello everyone. In this video we're going to begin chapter 10, which is about two-sample inference. And so to start off the chapter we'll talk about an intro to two samples and how it will differ from our inference of one sample that we had in the last two chapters. Then we'll talk very briefly about inference for two population proportions. Right? And then what we'll spend our substantial amount of time on is inference for two population means. Okay, we'll talk about what this two populations phrase actually means in the intro. Okay, and then inside of inference for two populations, we're actually going to talk about three different scenarios. Right, so the first scenario is independent samples where the variances are pooled. Okay, and so actually we'll talk about unpooled first, and so we need to talk about what pooled and unpooled variance means, all that good stuff we'll get to. And then we'll talk about dependent samples, which is often called a paired t-test. Okay, and so we'll talk about all these things in just a little bit. So to get started, when we talk about two sample inference, which really means we're looking at two different populations, why would we look at it? Well, it turns out many of the more interesting questions that statistical inference can answer are about two or more samples, which in turn mean two or more populations. And so usually if you're doing a t-test, or a lot of the heavy or hard sciences are into two sample things, you might see these types of questions. So let's get to it. First, a toy example. So one that really carries no actual weight to it, but is a valid two-sample sort of inference kind of question. Do sophomores or juniors have a higher GPA? Okay, now we can think about this problem, and if you invest yourself in it, you could ask, when you come in as a freshman, you have a lot of easy courses. You have a lot of your gen eds, but you also may not be quite as good of a student while you're as a freshman. So you come in and your freshman GPA, unless you really have a not great year, is going to be fairly high. But when sophomore year hits, you start getting into your major classes. The classes often become much tougher. And so usually in your sophomore year, your GPA is going to dip. The question is, on average, by your junior year, are you getting more and more classes in there, more and more gen eds, that your GPA will sort of rise, even if you don't do great, just by the fact that you have a number of classes. Okay, so you could think about this problem in an interesting way and get yourself into it. But that's a toy example that we would use statistical inference for, two-sample statistical inference. A more substantial question might be, will a new drug be effective at reducing high blood pressure? Okay, and so it turns out that's a two-sample problem, okay, that has some more substantial or real-world weight to it. Okay, but there are all kinds of questions in which we can answer with two-sample inference. Okay? The general strategy for solving these problems is going to be the exact same as our one-sample counterparts. Okay? The only thing that's going to change are the symbols and the assumptions. Okay? So we're going to have to switch in two-sample stuff for one-sample stuff, which really isn't going to be that challenging, and the assumptions are going to be slightly different. But all of the steps are going to be the same. Nothing really is going to change. Okay? You might not be able to see that at first, but hopefully by the end of the course, you'll kind of get a feel of what changes and what doesn't change, and the sort of jingle that everything goes by. Okay? So let's first start off with two population proportions. Okay? So we can do inference for two population proportions, right? And when we do that, we're looking at the difference between the two. Okay? And this is going to be true for two-sample means as well. When we want to compare two groups, the easiest way is to subtract the two and look at the difference. Okay? And so when we do inference, whether it's a confidence interval or a hypothesis test, really what we're going to be doing the inference on is the difference, P1 minus P2. If we have two population proportions, P1 and P2, the inference that we're going to do is looking at the difference between the two. Okay. So confidence intervals and hypothesis tests for the difference exist, but we're going to skip over them in this course. But I want you to know that they're there. Okay. They're less popular than two-sample inference for means. Usually you're going to do inference for means, but the two-sample proportion type of stuff does exist, and people do use them. It's just less popular, and we only have a finite amount of time. This is one of the sections that I tend to skip over. Okay. Anyway, so that's two-sample proportions. So we're done with that. Let's move on to what we'll spend most of our time on, which is two-sample inference for means. Okay? And we're going to start off when our two samples, and hence two populations, are independent of one another. Okay? Meaning one sample or one population does not affect the other population. That's not going to be true the entire time. Okay, but for the cases that we're looking at right away, it is. So let's get started. So our interest when we have independent samples is to make inference about the difference of two population means. Okay? If I can say that the difference between the two population means is greater than 0, that tells me something. Okay? Or if it's less than 0, that also tells me something. So for instance, if I look at the difference mu1 minus mu2, and I can say with some certainty that that difference is greater than 0, that's the same as saying that mu1 is greater than mu2. Okay? And so that's what I mean by we're looking at a difference and that we can make inference based on that is that sort of fact, that sort of sentence that I said. Okay? So let's look at the samples or the sampling scheme that is employed when we have two samples and they're independent. Okay? So we take samples of size N1 and N2 from each population respectively. Okay? N1 and N2 do not have to be the same. Okay? I can take a sample of size 500 from one population and a sample of size 1000 from the other one. That's okay. The assumptions that we have for both the confidence interval and the hypothesis testing kind of stuff that we have for this case, okay, the first case that we're looking at, are that you have independent samples. Okay, we're in the independent sample section, so hopefully that would be an assumption. But your samples are independent, meaning that one has no effect on the other. Okay? Could be sophomores and juniors. Because they're not the same people, they'd be independent. Now, if I took measurements when people were a sophomore and when people were juniors, if I took measurements on the same person, then those samples and hence populations would be dependent, right? Because they're the same person for both samples. But if it was different people, then we should be okay. Okay, independent samples. The first one that we're going to look at is unequal variances. Okay, and then both populations are approximately normally distributed. So there are three there: independent samples, unequal variances, and both populations are normally distributed. What I mean by unequal variances is that the assumption, or we're assuming, that when we look at the population distributions, if I sort of draw them on the same line here, if I look at sort of GPAs, okay, here's my red line, and then the sample or the population of sophomore GPAs might look something like that, where down here is maybe a GPA of 1. Up here is a GPA of 4. Okay. So that might be the GPA of sophomores. And in green could hypothetically be the GPAs of juniors. Okay, and if you look at these two, they are not equally spread out. Okay, if you look at this, the green has a much higher variance than the blue. Blue has smaller variance. Okay, it's got a higher peak and its tails aren't quite as heavy. And so, for example, in a case like when we looked at GPAs, it's actually probably a good assumption to have unequal variances because when you're a sophomore, you don't have as many classes under your belt. The GPAs are going to vary more when you're a sophomore, but as you take more and more classes, your GPA is going to settle in on a number. Okay, but they're going to regress to the mean, as we saw sort of before in our regression to the mean example kind of stuff. Okay, so that kind of behavior is going to happen, and juniors are going to have smaller variance than sophomores. That wasn't exactly what my picture was showing, but hopefully that idea gets across that in certain circumstances, you might want to assume that you have unequal variances. Okay, in fact, if you don't know anything about your data and whether or not it's safe to assume equal or unequal variances, you assume unequal variances. That's sort of the worst case. And so the methods that we're going to use are, in a sense, more conservative and will tend to cover more. When you have an equal variance assumption, which we'll see next week, in that case, you know more, and so your intervals will be tighter, your hypothesis tests will be stronger in a sense because you know more information. Okay, so that's enough of that rambling there. That's what unequal variances mean, and then both populations are approximately normally distributed. That's a general one that we usually see. Okay, so normal distribution. The statistics that you create for each sample that you take, you have a sample mean and a sample standard deviation. Okay, and then we get to the sampling distribution. For the one sample case, the sampling distribution of x bar was approximately normal, mean of mu, standard deviation of sigma over the square root of n, and when we looked at the standard error, it changed to s over the square root of n. Now, instead of just looking at x bar, the one sample case, we're now looking at the difference between the two, because that's what we're interested in making inference on. We're interested in mu1 minus mu2, so the sample that we're going to look at is x bar 1 minus x bar 2. Okay, and it turns out, which shouldn't be that surprising, that the sampling distribution of the difference is also normally distributed, okay, where the mean is mu1 minus mu2, and the standard deviation is this, the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so lots of formulas here that will be written down for you for the final. Okay, but important to remember these, okay, or this general form. And so consequently, when you change sigma to s when you don't know sigma, and so the standard error is s1 squared over n1 plus s2 squared over n2. Okay, great. So now let's move quickly to a confidence interval. Okay, so we're going to go through the steps of a confidence interval, then we'll do an example with Minitab, and then it'll be your turn. Okay, so again, we're estimating, or we're interested in estimating, is mu1 minus mu2. Okay, so that's what we're interested in inference, for inference here, mu1 minus mu2. Okay? And so the general form of a confidence interval, which is still true here, even though it's a two-sample deal, is the point estimate plus or minus some confidence factor times the standard error of the point estimate. Okay, and so as in the one sample case, the confidence factor is going to come from the t-distribution. Okay, and so alpha is found just like in the one sample case. So again, alpha determines the confidence factor. And then, if you'll remember back to the one sample case, it was a t-distribution. Alpha was important, and also degrees of freedom is important. Okay, and so for the one sample case, it was easy. It was n minus 1 degrees of freedom. But in this two sample case, it gets much more complicated. Okay, and so what's used in practice is what's called the Welch-Satterthwaite formula, okay, to calculate the degrees of freedom. And the degrees of freedom, if you're interested in the formula, that is the Welch-Satterthwaite formula, it looks like this, okay, and no one wants to calculate this, okay. So, luckily for us, the computer's going to do it, right? So, for each of these questions, we're going to have to use Minitab. There's no sense in trying to do it by hand. Okay, so with that in mind, and with the sampling distribution stuff that we learned in the last slide, our confidence interval formula is this: x bar 1 minus x bar 2 plus or minus some t times that standard error. Okay, so here's a summary. Excuse me. Here's a summary from the book that tells you a little bit about a confidence interval. And so if you need just one slide to help you look at it, this might be pretty helpful. So I just put this there. And so before we get to an example, we need to consider one or two things first. Okay, and so the interpretation of the confidence interval, not only do you make the interval, but I also want you to interpret the interval. Before it was easy, it gave you two numbers which were just on the same scale as the original number. So if it was GPA, the two numbers would be 2.9 and 3.4. And you knew that that is talking about GPAs between 2.9 and 3.4. But now when you're looking at the difference, you have to interpret it like you would interpret a difference. And so the numbers that are going to come out of this formula that that Minitab is going to give back to you are going to be something like negative 0.5 to 2.1. And that's not exactly on the scale of the original points, it's on the scale of the difference. Right? And so the magic number that you're looking for, or is sort of centered in your consideration, is 0. So before it might have been, if we were looking at a hypothesis test, you can actually make inferential decisions about a hypothesis based on a confidence interval. And the center of your sort of view should have been the null hypothesis. Well, now it's 0. Okay? And if all of the numbers, or the numbers in a confidence interval, are negative, then that infers that the first mean, mu1, is less than mu2. Okay? If 0 is contained in the interval, then that says there's no difference between the two. And then if it is greater than 1 or greater than 0, then that infers that mu1 is greater than mu2. Okay, so keep that in mind when we do the interpretation. Okay? So that's important. The other important thing is that the group labeling, mu1 and mu2, are arbitrary. Okay, meaning that they can switch depending on how you enter them into the software. And so keep in mind how you enter them, because that could change the output and, in fact, could also change your conclusions. Okay, so let's move on to an example. Suppose I'm interested in seeing whether men or women want more children. Okay, to this end, I've asked people the question, what's your ideal number of children for a family to have? The results are in the table below. Find and interpret a 95% confidence interval for the difference between the population means for males and females. Okay? So we're finding a 95% confidence interval for the difference between the population means. So first we need to write down some facts. And so I'm going to call group 1 mu1 the mean for men. Sorry about my bad writing. And mu2 the mean for women. Okay, let's make that look better. Okay, so mu1 is the mean for men, mu2 is the mean for women. Okay, and that gets us some more information. So the sample sizes, the sample size for men was 754, and the sample size for women was 921. Okay, the mean x bar 1 for men was 2.5, and the mean for women was 2.54. And then lastly, the sample standard deviation for men was 0.85, and the sample standard deviation for women was 0.89. Okay, so now we have all that information straight between the groups. Thus, I look for next the assumptions. The assumptions of the interval are the groups, or are the samples, sorry, I shouldn't say groups, are the samples independent? There was nothing in the problem that would make me think that they're related in some way, so yes. Okay, unequal variances. Also, we're going to assume yes because there's nothing that says that we could assume equal variances. Okay, and then last are the populations normally distributed. Again, there's nothing to say yes or no, but we're going to assume yes for now. Okay, so all the assumptions are met. Now we can use the formula. So the formula is x bar 1 minus x bar 2 plus or minus some t-score times s1 squared over n1 plus s2 squared over n2. Okay? I'm not going to make you write out all of this. At this point, what we need to do is actually go to Minitab, okay, and plug in the numbers and see what comes out. Okay, but when I do that, I'm going to lose all my writing because of the way I'm writing this. So I'm going to go through and I'm going to enter based on just like arbitrary numbers what would happen. So you'd work your way down and you'd get the numbers A and B. Okay, that would be your interval. And then the last part would be your interpretation. Okay, and your interpretation would say, I am 95% confident that the true mean difference between men and women actually the true difference between the number of kids men and women want is blank and is between blank and blank. Okay, so hopefully that makes some sense. The interval is talking about the difference, the true difference, or the difference in population means between the number of children that men and women want. Okay. So now with that being said, let's actually find A and B. And to do this, we're going to have to go to Minitab. So let's do that very quickly. Okay, here's our opening Minitab. We're going to go to Stat, Basic Statistics, and then 2sample-T. Okay, 2sample-T. So if we go to 2sample-T, it's going to give us a number of options here. Do we have actual data? And the answer is no. Okay, not right now, but we will later on. And so there'll be a lot of Minitab work in this chapter. We want the summarized data. Okay, and so here is our, here's where we can input all our stuff. Sample 1 was men. Okay, and so I'm going to flip back and forth very quickly here, so don't mind me. For men, it was 754. That was our sample size. And for women, it was 921. The sample mean for men was 2.5, and the sample mean for women was 2.54. And then the standard deviation was for men was 0.85. And the standard deviation for women was 0.89. Okay, and that seems to be right there. So there I've entered my data. I now want to go to options. Okay. Here we've got the confidence level, which is okay, I want a 95%. Okay, I don't care about this hypothesized difference because that only matters for hypothesis testing. Again, also don't care about the alternative hypothesis. And then down here, it doesn't mean anything to us yet, but I talked a little bit about it. Assume equal variances. You click that button if you can, but here we cannot. Okay, and so I click OK. I click OK. Okay, and then here we go. So it gave me a t-test, but I didn't want one. I only care about the confidence interval. Okay, and so here is the interval that I want. So the 95% confidence interval for a difference, okay, is negative 0.123, or maybe I should say negative 0.124 and 0.044. Okay, so that's my A and B for the question. Right? If I were to make some sort of statement based on this interval, I would say there is no difference because 0 is contained in the interval. Okay, and so I could try to make that inferential statement with a confidence interval. And actually, if you look down here at the test, it makes the same statement. If you look at this, the p-value is 0.348, which you would, of course, fail to reject that there is a difference. But that doesn't mean anything to us right now. We'll see that in just a second. Okay, so that's how you do a confidence interval for two population means where the variances are unequal. Okay, so that's our example. Now, your turn. Okay, so here's another example that I want you to do. Suppose I'm interested in investigating if the wage gap is still present in the United States. To this end, I take some samples here, and I want you to compute and interpret a 95% confidence interval. Okay, and so that's it for this video.